So this next chapter we move to is on vapor power cycles. It's probably the most practical, pragmatic, and actually the most direct and easy chapter in the whole textbook, really. It's vapor power cycles. It covers especially the way that it teaches us or shows us the way predominantly electricity is made throughout the world. Basically, you boil water from a heat source and make steam, pass it through a steam turbine. The steam turbine has a shaft connected to an electric generator, and you make electricity that way. So you burn something to turn a shaft to drive an electric generator to make electricity. This is a picture of a plant that you are co-owners of because you're citizens of the city of San Antonio or the greater Bexar County area. And basically a municipally owned utility, CPS Energy. And this is one of the power plants. You can see it's down by Calaveras Lake. For one of these power plants that, I forget the megawatt electric rating it is, probably anywhere from 700 to 1,000 megawatt electric. I'm sorry, I just don't remember. Typically consume about 1.5 train loads of coal a day. Train load is, I don't know how many cars, 70 cars or something. I mean, it's a lot. Don't quote me on this. I'm just saying there's a lot of coal that's shipped down to these power plants. And if you live near a railroad track that's bringing it in, anybody do? You know, seen any of the coal trains coming in? Anyway, they consume a lot of coal to burn, to create a lot of heat, to then transfer it in a boiler to steam, make steam, and then produce electricity. There's a lot of jobs at CPS Energy to hire mechanical engineers in this field. They either do the maintenance, or they do the repairs, or they do the scheduling, or they interface with purchasing to get a new power plant built. There's people who've graduated from our program who work for companies that specially design power plants throughout the world, throughout the United States, as well as students who graduated from our program who go and work for companies who specialize in building and getting them online, these power plants. So it's a very practical power cycle. So we're going to talk about the Carnot before we talk about the ideal Rankine vapor power cycle. So the Carnot is a word that you're familiar with coming out of the introduction to the second law of thermodynamics, true? Out of chapter 5, we talked about the Carnot gas power cycle. Tucked in there is also the Carnot vapor power cycle. Why do we talk about the Carnot vapor power cycle as a prelude or introduction to the ideal Rankine vapor power cycle? Well, it's really kind of a multiple choice question here. Is it because the thermal efficiency of the Carnot is greater than the Rankine, or that it's equal to the Rankine, or less than the Rankine, or Carnot discovered it before Rankine? What do you think? A. It's A. This is what I call the gold standard. You can't get any better than the Carnot cycle, but you're not even going to get as close as you might think you can to the Carnot cycle. These power plants that are running maybe 30% efficient, thermally efficient, that sounds pretty poor, doesn't it? Maybe 40% efficient, it still sounds pretty poor. And a lot of times you'll see people in the newspapers complaining, you're burning coal, and the dumb engineers can't even do better than 40% thermal efficiency. They're terrible. That means they're throwing 60% of that energy out into a lake or atmosphere or ocean, wasting it, just dumping it, wasting it. Well, you know, from the second law, there's a limitation on the transfer of heat into work. You can't get 100% conversion. And so this is a gold standard. It's the maximal efficiency based on the high temperature heat source and the low temperature heat sink. And what one equation do you remember? 1 minus Tc over Th. That's the maximum thermal efficiency based on a Carnot cycle. That works. That simple equation works for the gas power, and it also works for the vapor power cycle. You can't even get that close to that high of efficiency. You're below it when you have a practical Rankine cycle. And so we're going to try and distinguish the two. Well, little review on the Carnot. It's named after Nicolas Leonard Sadi Carnot. He lived 1796 to 1832. What do we know about those years in the history of the world? Yeah, the Industrial Revolution, beginning of it. Late 1700s was the beginning of the Industrial Revolution. Basically, he lived 36 years. He died a young man, in my opinion. When you get over 36, you'll agree with me. He was in Paris, France, and in 1824 he wrote one book in his life, and it's titled, it was written in French of course, but translated in English, Reflections on the Motive Power of Fire. Today you could still purchase a copy of that translation into English. I'm sure there's translations into other languages as well. I think this one's put out by Dover Publications. They used to specialize in reprinting old books. And here's a picture of him off of Wikipedia. Hopefully it's pretty accurate. I have no idea. But there's two main ideas that he came out with. He came out with the idealization of a heat engine. Basically, you have something that supplies heat, a high temperature thermal reservoir, going into a system, operating in a cycle, converting as much of that heat transfer, Q sub H, into work as possible. If you want to think about power, put a dot on them, that's fine, or amount. And you're going to have to throw some away to the ambient atmosphere, just the way heat engines work, and that is Q dot C. So the thermal efficiency is the power, mechanical power out over the heat from the high temperature source. Okay, so the main 2 points are that the efficiency is a function only of the two temperatures of the reservoirs. It's only a function of TH and TC, and we wrote that big equation down, 1 minus TC over TH. That came out of chapter 5 in our textbook, Thermo 1. That was very interesting result. So what you want to do is you want to have a high 1 minus TC over TH. So if you want to improve the thermal efficiency, what do you do to TH? Make it as high as possible. What do you do to TC? Make it as low as possible. That's essentially one of the big conclusions that came out of his work. The second one is that the maximum efficiency, the best you can do, the gold standard, so to speak, obtainable does not depend on the exact nature of the working fluid. You could do it with water, you could do it with air, you could do it with some other fluid, let's say helium or refrigerants, and the maximum is the maximum. It really isn't dependent on, well, the maximum with steam is this, but the maximum with this other special fluid that I want to sell you, some special fluid, will, no, the fluid's not going to change it, okay? So it's independent of the exact nature of the working fluid. Well, what is the Carnot vapor power cycle? This is the type of thing you need to just commit to memory if you haven't already. The cycle's made up of 4 components. The 4 components are a turbine, a condenser, a pump, and a boiler. You have maybe different names for these, maybe called a boiler or steam generator, but it's a boiler, okay? And the flow, steam comes out of the boiler and goes into the turbine. The steam that's out of the boiler we would call state 1. We would know its temperature, pressure, its enthalpy, its entropy, stuff like that. And then after the turbine, it's going to come out and go to the condenser. We call that state 2. The purpose of the turbine is to generate as much power out of the turbine as possible, or as much power out of the turbine per unit mass flow rate through it, which we then abbreviate to lowercase WT. So the funny units on this, either we're talking about kilowatts of power, or we're talking about kilojoules of power per kilogram of steam flowing through. Hopefully the 2 natures of that discussion are similar. Lowercase w subscript t, specific power out per unit mass flow rate through. Units, kilojoules per kilogram. All right, so state 2 is going to come out lower enthalpy, lower pressure, lower temperature, But then through the condenser, it comes out of the condenser. It's ready to go into a pump. That's state 3, feeding the pump out of the condenser. After the pump, it goes up. At state 4, it's ready to go into the boiler. So we have 4 components, and we have 4 major states of the steam between the components. All right, let's talk about the easiest property to distinguish between these 4 properties, or these 4 states. The easiest property is pressure. Easiest property is pressure. Okay, in the boiler, is the purpose of the boiler to change the pressure of the steam, or is the purpose of the boiler just to add heat to the steam? In the boiler, you're bringing in Q dot from a high temperature source. Let's call that Q dot B, or lowercase QB. You can do the same thing. It's either kilojoules per kilogram, lowercase QB, or Q dot B, which would be kilowatts. All right. So we're bringing in heat in the boiler. Is there any shaft work going into the boiler? No power into the boiler. It's just heat transfer into the steam. Tell me a little bit about the pressure. Does the pressure decrease, stay the same, or increase roughly? The pressure going through the boiler. Well, let's do this one. Let's talk about the pressure going through the turbine. How about the pressure on the outlet of the turbine compared to the pressure on the inlet of the turbine? Which one is greater? Which one are they equal? The pressure on the inlet to the turbine is greater than the exit of the turbine. True? Let's do the pump. How about the pressure on the exit of the pump compared to the pressure at the inlet of the pump? Is it the same pressure, higher pressure? No, it's a higher outlet pressure. Now, there's 2 heat exchangers. One's the boiler, one's the condenser. Does the heat exchanger change the pressure of the fluid going through it? This is one of the things you think about for a long time, but you find that the outlet pressure is essentially the same as the inlet pressure. If you have a little friction, fluid friction, some resistance to the flow, yes, we're going to have, just like flow in a pipe, you're going to have some pressure drop in the pipe. But we're neglecting that in this class. When you get to a real power plant, you really want to analyze everything. The design engineer has to accommodate fluid mechanics and thermodynamics and heat transfer all together, and probably some other material properties and other things in the design and analysis of a real operating system. But this is a very good approximation. We have a huge pressure drop across the turbine. We have a huge pressure gain across the pump. We have a negligible pressure change through the 2 heat exchangers, through either the boiler or through the condenser. This is P2. So how many distinct pressures do I really have in this system? 2. The high pressure side, where's the high pressure side? Split it right there. That's the high pressure side, pressure high. And the low pressure side, pressure low. Just 2 distinct pressures. That's helpful. All right. You have, for each device, you have either the primary transfer is either heat transfer or a work transfer. We've already talked about this red line makes it this hard there. I'm going to try and draw it like this. Is you talk about the turbine, the primary purpose of the turbine is to produce what? Work out. Okay. The primary purpose of the boiler, bring in heat. How about the condenser? Reject heat. So Q dot condenser. Now, we're going to get bogged down a little bit. Are we going to have the traditional sign convention in thermodynamics applied to each component? If it is, then we would assume Q dot into the condenser from the surroundings, and then we would calculate a negative Q dot. Well, or you can say I'm going to abandon the sign convention because I know that the heat transfer to the surroundings is out of the condenser. So either way, you got to just pick one and stay with it. And then lowercase q sub c if you put it on a per unit mass basis. How about the pump? Same discussion. Is the pump primarily a work-consuming device? Sure. And it's negligible heat transfer. So I'm going to draw it like this. I'm going to put the W lowercase p going in. And I'm going to put kind of a hash mark here saying that the It's adiabatic. Same here, adiabatic. Okay, right. So that's our basic Carnot power cycle. What are we interested in? We're interested in metrics. There's really, I think, 3 metrics. One is kind of almost obvious. You're going to have a lot of mass flowing around in a loop. See that m dot? And you're going to try and produce net power out. So what you'd like is W dot net to be large compared to m dot. Well, what's another way of writing that is lowercase w net. You want the specific work out per kilogram that goes through each component to be as high as possible. That's a good metric. All right. What's another metric? You would like a high thermal efficiency. What's a thermal efficiency? Well, the specific work out, net work out, right? Divided by what you have to feed to drive the system. You have to feed the boiler. You don't have to feed the condenser. That's just the way to reject heat. So you divide it by QB. Every now and then a student will put, isn't the thermal efficiency work net divided by Q net? Is Q net the same as QB? No. So what happens if they actually put work net divided by Q net? It's 1. That should raise a red flag. Hold it, thermal efficiency is 100%. That's all you're saying is you accounted for all the energy flow. So it's not Q net, it's just what comes into the boiler, into the working fluid in the boiler. And the other metric is the BWR, back work ratio. That says the turbine produces something. This is WT. That's what comes out of the turbine. Some of what comes out of the turbine has to go back and feed the pump, WP. What percent of the power out of the turbine feeds the pump? True? Do you see that as a good metric? So let's ask this. What would be good? What would be good for all 3 of these metrics? Would you like a high or a low work net, the specific work net for the cycle? What would you like? You would like it high. All right. How about the thermal efficiency? Would you like it as a design engineer, high thermal efficiency or low thermal efficiency? You'd like it high. How about back work ratio? Do you want a lot of that energy out of the turbine feeding back into the pump? No, you want that as low. So that's the kind of design goals. Let's make this one metric high, make this metric high, let's make this metric low. All right. Well, how do we calculate some of these things? What is W sub T? Let's just analyze. How would I calculate W sub T? I would do an open system analysis, a control volume around that turbine. It's operating steady state, negligible changes of kinetic potential energy, sort of standard assumptions. And it has no heat transfer. And you're going to find out it's just going to be boiling down to a change in the enthalpy. True? All right, let's do this. Let's go and do the Q around the boiler. Do a first law analysis, open system around that boiler. Is there any shaft work? No. No negligible changes of kinetic potential energy, operating steady state. What's brought into, that's a bad looking B. Let me try and redraw that. Q sub B is going to be H1 minus H4. Does that make sense from the first law? All right, now let's go down and do the condenser. WC, not WC, QC. What about QC? Depends on the direction that you assumed for the transfer. If you want to stay with the, let me do this. I'm going to put over here Q sub C traditional, which would be positive in, which we know it's not in, so it's going to be a negative quantity, right? If you do either one, there'll just be a sign switch between the two. Let me do it this way where I'm showing it positive coming out. If it's positive coming out, H2 minus H3. Do you agree? How do I do that? Well, I know the enthalpy coming into the condenser at state 2, H2 is greater than H3. You're rejecting some heat out of the steam, so H2 is greater than H3. So if you come over and do the traditional, you would get H3 minus H2, and that's going to be a negative quantity. Okay, how about W into the pump? Which enthalpy is going to be greater, H4 or H3? H4 is greater. So it would be H4 minus H3. And if you went over here and said, no, I'm going to do the traditional, it's power out of the control volume, power out is positive out of that pump, well, then you're going to get H3 minus H4, and that's going to be a negative quantity. All right. Now, we know how to get all of those. So what is W net? It'll be the work out of the turbine minus the work to drive the pump. Or, if you want to do traditional, it'll be the work out of the turbine plus work out of the pump. But WP is negative on that one. Yes?
So like on a test, would you want us to make the values going out?
I'm going to look, just like in statics class, I'm going to look at your illustration and see which direction you showed. Because in statics, remember, you could assume a particular direction. I'm going to assume F1 is this direction. Somebody else comes in and they're going to say, no, I'm going to assume F1 is in that direction. Well, you, by your free body diagram, showed the positive direction of your assumed force or reaction or something. Okay? So that's really what I'm going to look for. And so as long as you're clear, I can follow your work and grade it accurately. But I just alert, it's easy to be with a negative sign, error. You don't want that, right? So kind of pick one and stay with it. So we know how to calculate this first metric, and then we know how to calculate this second metric bound to the enthalpies, and the same with this backwork ratio. Notice, if this backwork ratio, if you're using the traditional, you may have to put a negative W sub P divided by WT. If it's traditional, you may have to put a negative sign on that WP because it's a negative entity. All right? All right. Well, we can use diagrams to help us understand the Carnot cycle. The property diagram of interest is the temperature entropy diagram. When you're talking about limitations on the transfer of heat into work, you're talking about heat engines, the great diagram is the temperature entropy diagram. What does the dome look like on the temperature entropy diagram? Fairly symmetric. What's that dot at that top of the dome? What's that called? The CP, the critical point. You're exactly right. What is every state off to the right? Saturated vapor. And then what is every off to the left? Saturated liquid. And so what do we want from a Carnot cycle is we want every component to be internally reversible. We want sigma dot in the turbine to be 0. What was sigma dot? No entropy generation. We want it to be completely frictionless, completely reversible expansion through that turbine. That makes sense. I'll get the most power out. How about sigma dot over in the pump? You want that to be reversible. So for the cycle, everything internal to the cycle needs to be reversible. The pump and the turbine need to be reversible. We also not only have it to be internally reversible, we need it to be externally reversible. How it interacts with the surroundings, we need it to be reversible. Where does it interact with the surroundings? Primarily in the heat transfers, in the boiler and in the condenser. And in the boiler and condenser, you want heat to come into the working fluid reversibly. Well, what's one of the sources of irreversibility? We understand friction as a source of irreversibility. We understand expansion through a finite pressure difference, unrestrained expansion through a delta P. You also have heat transfer through a delta T. If you have a heat transfer from high temperature to low temperature, that by nature is irreversible. How do you make it less irreversible? You make the delta T smaller, 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 smaller. So in the limit, the temperature is constant and equal to the working fluid is equal to the heat source temperature. So that we talk about the temperature of the heat source and the temperature of the working fluid being the same in the boiler. Let me repeat that. The temperature of the heat source that's supplying heat to the boiler, or the working fluid, that's steam in the boiler, is TH. And the temperature of the steam in the boiler is the same TH. And this is one of those oxymorons. It makes no sense to students. It makes no sense to somebody you're going to explain, hey, what did you learn in thermodynamics? Well, let me try and describe this to you. And they're going to listen to you a few minutes and they're going to say, you're ludicrous. You don't know what you're talking about. You're going to transfer heat into something like water. Yep, that's what you're going to do in the boiler. And the temperature of the water's not going to go up? Impossible. You paid UTSA way too much money for that degree of yours. Get your money back while you can. Right? Well, think about this. If I'm going through the boiler, point 1, point 2, point 3, point 4, point 5, point 6, I'm just a bunch of points going through that boiler. You mean as I add more and more heat to the working fluid, the temperature of the steam is not changing in the boiler? Is that possible?
Yes.
What's the magic? You're in the dome. You're adding heat at constant pressure, and all you're doing is changing phase. That's all you're doing. You're just boiling it. And so you're in the dome. So somehow, if you can bring in at a high pressure, let's show a line of high pressure on this TS diagram. Doesn't it look like this? And the magic is it's a flat line in the dome at constant pressure. So if I could bring it in at this state, state 4, which is saturated liquid, take it out at this state, which is state 1, saturated vapor, I added a lot of heat, but the temperature didn't change. And if it matches the heat source, heat source is equal to the TH of the water boiling, no external irreversibilities, the perfect Carnot cycle. Right? Got it. So that helps us to understand that. It goes from saturated liquid to saturated vapor at high pressure. But what happens when we go through the turbine? We're going to go from state 1 to state 2. Where is state 2 on my temperature entropy diagram? You do a second law analysis, just like we did the first law, around that turbine. Sigma dot's 0, no irreversibilities. Q dot 0, there's no entropy transfer because there's no heat transfer. It's adiabatic expansion. Adiabatic reversible expansion of steam is isentropic. Adiabatic reversible expansion of the steam is isentropic. So where is state 2 compared to state 1? Straight down. See, S2 is equal to S1 from the second law analysis of that turbine. So it's straight down. How far down? Well, go to the lower pressure. Here's our lower pressure line. Pressure low. This is pressure high. So state 2 is right there. Is it saturated liquid, saturated vapor, superheated vapor, subcooled liquid? What is state 2? Describe the state. It's two-phase liquid-vapor mixture. It has a quality at state 2. What is X2? What is it defined as? Quality is mass fraction of the fluid that's in the vapor state. mass fraction that's in the vapor state. True? That's quality. Looking at that diagram, can you estimate the quality at state 2? 60, 70%? Does it look good? Now, 1 to 2 is easy. 2 over to 3 is a little trickier because I need to figure out where 3 is. But where is state 3? You're going through the condenser. It's going to be somewhere over here, isn't it? How far over do I put state 3? Directly underneath 4. And this takes you a while to figure out. How did you know to put 3 directly under 4? You've got to work backwards through the pump. You think about doing a second law analysis around that pump. There's no heat transfer, hence no entropy transfer with heat. It's sigma dot equal to 0. There's no irreversibilities. There's no entropy generation. And we find that S4 is equal to S3 or S3 is equal to S4, either way. But conceptually, I kind of work backwards from state 4 down to state 3. So those two S's, S3 equal to S4, and S1 is equal to S2. They have the same entropies. What does this cycle look like on a TS diagram? A nice rectangle, a nice box. That's what it looks like. All of the heat is brought in at the high temperature, TH. All of the heat is rejected at the low temperature, TC or TL, whatever notation you like for the low temperature. TC for cold or TL for low. Make sense? That's our TS diagram. Armed with that, we can then solve some problems. But before I solve a problem, I wanted to show a temperature entropy diagram drawn to scale using software. This software is called RefProp. It's produced by NIST. I mentioned it before, National Institute of Standards and Technology. It's basically a federally funded government agency. And you can download a student version that has Steam in it, and you can make a plot like this. And it's pretty powerful software. Maybe I'll show it to you more later. But this is a plot generated, and you can make this plot, no problem. Just learning the software, and it's not that hard. Temperature entropy diagram, drawn to scale. Here's 100, here's 200. Those are all degrees C up to 700 degrees C. That's pretty hot, right? And then the values of the entropy really are not physically intuitive in any way, but they match up with the steam tables that are in your back of your book. So if we said we wanted to have, and I'm going to solve a problem where the boiler pressure is 8 megapascal. This is a line at 8 megapascal, and it goes just like that, okay? And then we wanted to come out at a condenser pressure of 20 kilopascal. Is that 20 kilopascal? Can you see that number? This is a line at 20 kilopascal going across. Okay. One thing is this line, let me see if I can show it right here, is going across right here is, here's 100 kilopascal, there it is, going across. What does that line up really closely to? That's right, atmospheric pressure, 1 bar, which gives us a boiling point temperature of 100 degrees C. Close, it's 99 point something, okay? So that's matching with the 100 degrees C right there for reference. So, when you talk about a 20 kilopascal condenser pressure, is that in a state of vacuum compared to the local ambient pressure of 100 kilopascal? Sure, it is. Okay. So this would be our different states. Let's go ahead and put on state 1, saturated vapor coming out of the boiler. Expand to state 2. Now you can see if I'm drawing this to scale, it looks like it's a little less than 75% quality at state 2, right? This is a line of constant quality right here of 75%. Okay. State 4 is right there. Come over here. State 3 is right there. That looks like it's around, this is 25% quality. It looks like what? 30% quality. It's state 3. There's our cycle drawn on a TS diagram using the software RefProp, hopefully to scale or to scale. Pretty good scale. Make sense? Very good. So this is the problem. The boiler pressure is 8 megapascal. The condenser's 20 kilopascal. And you want to calculate part A, B, C, D, all of this for the Carnot vapor power cycle. Well, how am I going to do this? I would say from memory, make a sketch of the system with the 4 major components. I know that we just did that. You have the turbine, you have the condenser, you have the pump, you have the boiler. If you want to put them anything other than a box, go ahead and put them as a box. Maybe you visually know what a turbine looks like, and so you draw it some with a different shape to it. But you can put a box for these. And then go ahead and put the direction of the flow between them, and then label your states. And I encourage you to just adopt the textbook's notation for the labeling of states. Put 1 there. It doesn't matter. You could put 1 anywhere. But once you put 1 there, put 2 as the next one in the loop, and then 3, and then 4 in the cycle. So states 1, 2, 3, 4. Notice that when you plot this on a temperature entropy diagram, 1 kind of goes in that corner, 2 in that corner, 3 in that corner, and state 4 in that corner. And there's your box on a temperature entropy diagram. That's one of the reasons they picked to lay it out that way. That makes sense? All right, so the upper right, the lower right, the lower left, and the upper left corners on that. Make a table for your properties. So a property table. How many states do I have to worry about? 4. Okay. If you're going to do an exergy calculation, put state 0, dead state, you'd have 5. But I would do this. State number 1, 2, 3, 4. And then just put the properties in the order basically the textbook labels them at. Pressure, temperature, specific volume, internal energy, enthalpy, entropy, flow exergy. Okay? Now, you might say, well, the specific volume, maybe I need this tuck in quality right there. That's fine. Tuck in quality right there too. Okay? Because 2 of the states have a definite quality between 0 and 1. All right. So I would do this. I would put my units for the pressure and all that up here. And so maybe I put this in kilopascal. I'm running out of room. Put this in degrees C. Quality is dimensionless. Meters cubed per kilogram. I'm trying to not use up all my space. But you know, when you have a pressure, go ahead and put your units maybe in the column above. That way, every number down there, you don't have to put the unit. So I come down, and now I have to convert 8 megapascal to kilopascal. It's 8,000. So state 1 is at 8,000 kilopascal. What other is at 8,000? What other state is at 8,000 kilopascal? State 4. The pressure is the easiest. And then what about the 20 and the 20? That's at state 2 and 3. But when you're doing this, make sure you're thinking through. Oh, why? There's no pressure change in the boiler. There's no pressure change in the condenser. I only have really a high and a low pressure. Now we think about the temperatures. What about the temperature at state 1? It's the T-sat at that state 1, which is the pressure at P1. So I go look that up. I'm not going to look it up right now. I'm going to give you the numbers in a minute, but do you see what we're doing there? What about the temperature at 4? T-sat at P1. That's the same pressure, same saturation temperature. These are the same. That the red, they're high temperatures. What about these 2 temperatures for state 2 and state 3? Are they the same? Sure. And are they the saturation temperature at the condenser pressure? Are they the Tsat? And like this is Tsat, but this Tsat is at the boiler pressure. This is at the condenser pressure. Are they? Yes. They are. So this is Tsat at the condenser. Both of those. Make sense? Yes.
I thought you said saturation was X is either 0 or 100.
Well, you could be anywhere around here, anywhere. It's like between 4 and 1 when it's going through the boiler. Does the temperature of the steam change as it's going through that boiler, as I'm going through and changing phase? No. So anywhere between 4 and 1 along a line of constant pressure, you have a constant temperature. Make sense? All right. Now, what about the quality? Let's do the quality. At state 1, it's 100%. At state 2, it's some fraction that we're going to have to work on. State 3, it's some fraction we're going to have to work on. And state 4, it's 0. See the quality? All right. Then V sub G, U sub G, H of G, S of G, all of those come from saturated vapor. State 1 is easy, isn't it? State 4, V sub F, U sub F, H of F, S of F, all saturated liquids values. True? Now, I'm not going to worry too much, but when I show it to you, I'll show you the flow exergy in the calculation, but I would have to calculate the dead state properties and the flow exergy values. But let's skip it for now. All right, now, what really, this is a thing I put over here to help me, is I put what is a little notation to help me fix state 1. What really fixed state 1? Knowing 2 pieces of information, the pressure at 1, and that it was saturated vapor. So the pressure and the saturated vapor, or another way of saying it, the quality. How about for state 4? The pressure and knowing that it's saturated liquid. That filled in the rest of the properties. I can do the work. I could get the rest of the properties for state 1 and 4. But now for state 2 and state 3, I have to think about it. How did I fix state 2? How did I know state 2 is straight below on a temperature entropy diagram state 1? It was isentropic. I had to do a second law analysis around that turbine. There was no entropy generation in the turbine, and there's no heat transfer in the turbine. It's isentropic expansion through the turbine. So right here, I say that S2 is equal to S1. So guess what 2 independent intensive properties fix state 2? Pressure and entropy. So pressure and entropy fix state 2. I have to be able to go and get all the other properties as a function of P and S. I'll need to get V as a function of P and S, U is a function of P and S, H is a function of P and S. Because it's 2-phase, the first thing I'm going to do, just to let you know, is to remind you, is I'll get quality at state 2, which is S2 minus S of F divided by S of G minus S of F. But those S of F and S of G are the saturated values, saturated liquid, saturated vapor values, at the condenser pressure. At the condenser pressure, true? I'll get that quality. And when I get that quality at state 2, if I have a diagram like this, it better be a little less than 75% or I made an error for this problem. All right, that's how I get the quality at state 2, and then I get the specific volume at state 2, the internal energy at state 2, the enthalpy at state 2. The U's are not needed for this problem. I put them in there for completeness. But how do I get, let's say, H2? That's going to be H of F plus the quality of state 2 times HFG. Good. How about for state 3? This is the hard one. This is the one that we had to work backwards from. Even though the flow is going from 3 to 4, conceptually we work backwards through the pump from 4 back to 3. What did we conclude about S? S3 is equal to S4, the same entropy. Pressure and entropy, fixed state 3. The same process. I'll get the quality of state 3. Then once I get the quality of state 3, I'll get the other properties. Get the property tables. Can you see how you can get every property for all the states? And then make another table for the components. The component table, the device table. How many components are there? 4. What are their names? Turbine, condenser, pump, boiler. Think about the heat transfer per unit mass and the work per unit mass going through each of those devices. Now here you have to pick and choose. Are we going to stay with traditional sign convention? If you stay with the traditional sign convention, the Q into the boiler, this is the Q into the boiler, is definitely positive. See that? But what about the Q into the condenser? Hey, we said the Q into the boiler, the Q into the condenser. Hey, it's not into the condenser, it's out of the condenser. But if you're going to stay with the sign convention, what do we know about into the condenser? It's negative. Just to alert you to the sign. Right? Now let's think about the work. The work was out of the turbine. That's going to be positive. But what about the pump? It's going to be negative. Okay. How about these other ones? What is the assumption about the turbine? Is it a heat transfer device? No. It's adiabatic. There's no heat transfer. How about for the condenser? There's no work. How about for the pump? There's no heat transfer. And how about for the boiler? There's no work. So 4 of those are 0. And then you have 2 Q's and 2 W's. 1 Q is positive, 1 negative, 1 W is positive, 1 is negative, and that you can figure out beforehand. But now that you've figured it out, what is the W for the turbine? It's just going to be related to a change in enthalpy. It comes in at high enthalpy, goes out at low enthalpy. And that's the work out of the turbine. First law for the turbine. What about this one right here? This is the Q into or out of, I'm going to put into the condenser. And it's going to be negative, true? All right. This one is a little trickier for me because I like to work it with the positive quantity. But what about H2? H2 is greater, so it's going to be H3 minus H2. That'll be a negative answer. All right. How about for this one, which is the work out of the pump? Out of the pump. That's even hard to say. Work out of the pump will be H3 minus H4. And then the last one right here, the Q is the boiler. And so I see that I'm running out of time. Let me just finish this one. It'll be H1 minus H4. All right. Well, I didn't intend to stop here, but that's where I stopped. I need to give you back your exams. I'll do that right now. Thank you for your attention.